Okay, so due to the limitations of the binder format, which involves low amounts of memory, you can only use about 2 gigabytes of RAM before it kills your process. We're going to do an assembly of a genome and not a metagenome. Metagenomes typically involve very large sequence files and a lot of memory to be used. Especially if you're doing error correction. One of the reasons people prefer megahit a lot of the times to Spades is that the memory usage of megahit is much lower than Spades. Here I am going to use Spades because that's what I use most of the time, and I hope that someone who is an expert in megahit will do a little tutorial on megahit so that I can learn the best way to use it. But for now, what we're going to do is pull up the demo, open the terminal if you haven't already, and cd into the data directory. And here I've done the cooking show thing and have already done the calculations, but we'll run through each of the steps here in the script, which is under lesson 5 in the file demo 5.1 spades.sh. Excuse me. So the first thing we're going to do in this case is get our files prepared for the assembly. In this case, the files are in a zip format, fastq.zip. And what we're going to do is unzip those, re-zip them as fastq.gz files, and save them under a different name here so that we can use them in the downstream process. So you can just copy and paste that to do that. I've already done it, so I can't do it again to show you, but the idea here is that we have a number of different sequences of related genomes. In this case, it's a Delta proteobacterium. And we're going to do a number of different assemblies of these sequencing data sets in order to compare the assemblies together. So the output from doing these things will be these two fastq.gz files, dvh.1 and _2, which are the going to be the reference, and then these, which are downloaded from the sequence read archive, which will be used as comparisons. So in the script, you're provided a loop to do all of these one after another. In this case, I'm going to step through them one by one. So I'm going to, oops. Use my little loop here to assign this variable prefix to each one of the data sets in turn, and then we'll go through each one of those. So right now, our prefix is set as SRR 5780889. Now we're going to use this little bash variable assignment to assign the reads, the forward reads and the reverse reads for each of these data sets, and use those in the downstream process. So now we have the forward reads assigned as this variable R1, the reverse reads are assigned as R2. And like we've done before in the past, we're going to do some quality control cleanup before we run our assembly. So the first thing we're going to do is to trim the adapters. So we're going to use BBDuke like we've done before, using the adapter references that are built into BBDuke. And if you haven't seen this before, you can go back a couple of lessons ago in the metagenomics track. We went into these tools in more detail. So we have our reads. We trimmed a few reads, not too many. It was a pretty clean data set to begin with. This next step is to remove artifacts and any viral DNA that's left if it was sequenced alongside viral DNA. Here again, we remove a few reads and a few bases, but not too many. The next step, we're going to do another quality trimming step based on the quality scores in the FASTQ files. So again, we've discussed this before, but we're going to trim any base pairs that have a quality score lower than 10, for example. We're going to throw out any reads that have a length less than 70, that have any ends at all, that have low entropy or low complexity reads. And all these steps are rather important for good quality assemblies. So it's important to do those steps. Another step that's very important for metagenomics, especially, is to do some kind of error correction. And unfortunately, I couldn't get any of the error correction tools to run on the binder due to the memory limits, but we may have a special look at them at some point in the future where we go into them in a little bit more detail. Like I said before, Spades has a built-in error correction module, but it is extremely memory intensive. So, so you can easily use a terabyte or two of RAM in these error correction steps. BB Tools also has error correction built into various steps. I think Tadpole is the assembler in BB Tools, and it's also the one that the author recommends to use for error correction. So you can try that if you want, or if you have another error correction tool, you can apply that as well beforehand. Okay, here we have our quality trimmed reads here in this file, qtrim.fq.gz. And then this Tadpole assembly I tried to do also failed, and I forgot to take it out, I'm sorry. So we're just going to do the Spades assembly in this case using the quality controlled reads. So Spades is installed on the binder as spades.py. Spades takes at least one output here, or sorry, it takes an input, which is the output directory. So in this case, we'll put it in the prefix directory and add a little Spades to it. There's also various ways to input your reads into Spades. So we can get to the help by just running spades.py and look at some of the ways that you can input your data. So the easiest way is if you have interlaced FASTQ files that have both the forward and the paired end reads together, then you can use this flag --12. Otherwise, if they're separate, you can use the flag -1 and -2. If you have unpaired reads, you can use them as well. If you have merged reads, you can use them as well. Those are when you've overlapped your paired end reads into a single read. And then if you have multiple libraries, you can also include all of them separately using these flags where you tell the assembler, this is the forward paired read for library number hashtag, and you give it the file name. It also takes mate paired reads. Those are, I think, typically more for eukaryotic genomes. High quality mate pairs, I actually don't even know what that is. Probably eukaryote people do. If you have good contigs, for example, from Sanger sequencing, you can include those as well. If you have nanopore or PacBio data, you can include those as well to do hybrid assembly. Some of the options that are available, we're going to do this one. We're going to do only assembler. As I mentioned, the error correction step is very high memory, and we don't have the memory here to do that. You can also just do the error correction in Spades, and it'll output the corrected reads without doing the assembly. There's also a mode useful for isolate genomics called careful mode, which tries to reduce the number of mismatches and short indels by going through and double checking all of the contigs. Most of the assemblers that I know of are all checkpointed, so that if, for example, you put it onto a cluster and you run out of time and the cluster kills your assembly before it's finished, you can usually continue the assembly from wherever it left off, or if you want to restart it from a specific spot, you can do that as well. And then there's a few more options to use with Spades. For example, you can specify the number of threads to use. If you don't want it to use every thread on your machine, you can tell it how many to use. You can specify a memory limit. And for Spades, it's important to know that this doesn't actually tell Spades not to use more memory than this. It just tells Spades to crash gracefully if it would otherwise use more memory than this. So unfortunately, you can't force Spades to run an assembly that fits within the memory you have on your machine. It's just a way to make sure that it doesn't crash your machine if it exceeds the amount of memory that you have. The tempter flag is useful, I've found, when I'm assembling in a directory or on a file system from a file system that doesn't have enough memory. So you can specify, for example, the scratch folder will store all its temporary files. And then the other one flag that's commonly used is K, where you tell Spades what k-mers you want to use. So if you don't specify what k-mer lengths to use, then it will choose its own given your read lengths and its own decision making. But if you, for some reason, have already done some iteration and parameterization and you know exactly which k-mers you want to use, you can tell Spades to use those k-mers and it will. Finally, the options up here will tell Spades in what mode it should run. And so there's a number of different options, and mostly they have to do with what your coverage profile looks like. So if you have high coverage data that's from isolates, for example, where you have probably high coverage and high evenness of your reads, you can use this flag and it will run in a quick mode that gets you a nice assembly very quickly. If you have single cell data, which is originally what Spades was written for, so this is when you do, for example, multiple displacement amplification and amplify a single genome many, many times and then sequence that. That data tends to have kind of weird coverage profiles, and so Spades can use that information in single cell mode. It also has a metagenomic mode, which uses shorter k-mers than the isolate mode, and also does some different decision making when it sees multiple strains, for example, when there's strain variation in your data set. It will try to merge those in a reasonable way so that you're not overwhelmed with contigs, but that you can still get a good assembly when in the presence of strain variation. There's also some other modes that Spades will run in that I haven't played around with too much. But for example, if you're if you're assembling RNA-seq data to get longer contigs, you can assemble it using the RNA flag. There's a specific flag for assembling plasmids, and the Spades authors have papers describing each of these if you're particularly interested in them. Okay, so that's a quick run through of Spades. Now we're going to run Spades using the only assembler flag that we looked at earlier that will preclude the error correction step. And we're going to input the quality confirmed files that we generated with BBMap. Okay, so we're going here. You can see that we didn't specify any of the particular modes. We didn't specify isolate or meta modes. So it's just running in the default mode, and it warns us that if we're assembling an isolate, maybe we should have used the isolate option, and we could try that if we wanted to. It's selecting the k-mers automatically based on the read length. Let's see here. So the read length it chose, or sorry, the k-mer length it chose are 21, 33, 55, and 77. If you had an interest in changing those, that's very easy to do. So Spades is very verbose. It tells you a lot about what it's doing as it's doing. Here it's started the assembly. It's starting with a k equals 21. And here it's reading in the reads and doing the De Bruijn graph construction. It's finding all the k+1 mers and generating the nodes. It's doing k-mer counting and some indexing. It's doing more extensions of the k+1 mers. I didn't mention it earlier, but there are, besides bubbles, another common structure in De Bruijn assembly graphs are tips. So those are pieces of DNA that are essentially sticking off of the main assembly. And so a very common step in De Bruijn graph kind of assembly cleanup is clipping those tips. So going through and finding out these extensions that are kind of dead ends and clipping them from the assembly. Oops. So a large part of the assembly process is that kind of graph simplification. So you can imagine, even in that small example we used with 10 reads, there was a lot of nodes and a lot of edges. And you can imagine that those assembly graphs get very complicated very quickly in the intermediate steps. And so a lot of the process of any assembly pipeline is not just producing that graph. None of the software just spits that raw graph out at you. There's always heuristics in there to try and simplify the graph and get closer to the truth. And that's one thing I should emphasize, is that any assembly that you do using raw reads is best thought of as a hypothesis rather than the truth. There are a lot of possibilities for misassemblies where you have chimeras, especially in metagenomic assembly, where two different genomes, maybe they share a small stretch of k-mers and they get misassembled together into one long contig that is actually a bad estimate of what is actually in the environment. So when we look at the quality control metrics, one of the ways that you can do that is to compare your contigs against a reference, if you have one, and estimate the rate of of production of chimeras or misassemblies. And that can be very useful in evaluating your quality of your assembly and how well you expect your hypothesis to function. Okay, so pretty quick, it finished k equals 21 in 1 minute and 4 seconds, and then it moves on and does k equals 33. Using the data, using the assembly of k equals 21 as one of the inputs to the next stage. So it's an iterative buildup of the graph over the k-mer lengths. Dun, 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 dun. Finished k equals 33, k 55. You can see that even with this tiny genome, it used or requested 11 gigs of RAM for a fraction of a second. And you'll often see that, especially with larger metagenomes, that the RAM requirements are out of this world. Okay, we're done. Let's go look at the output from Spades real quick. What do we have here? We have some intermediate files from each of the k-mer lengths, and you can get rid of these. I think Spades has gotten better about keeping around unnecessary files, so they may not take up a lot of room, but if you're using older versions of Spades, they essentially kept a complete copy of all the data at each step. So you want to erase those. The assembly graph comes in a couple of different flavors you can look at. One is called a FASTG file, which is just like a FASTA file, except it maintains the config connection data in the FASTA header. So if you were to just look at the headers of this file, you can see where the edges are that connect the graph, and take a look at that. There's various software that parses those FASTG files. A more efficient data structure is this GFA format. Oops. Which encodes the data in a somewhat different way. So here are the contigs, excuse me, with all of the data. And then here are the links, the edges between the contigs. So it's showing you, there's a link here between contig 112349, the positive sense, and 132589. Among them. So you can, there are other software packages that parse this data to reconstruct the assembly graph for visualization. The one I often use is called Bandage, but you can also import these into programs like Cytoscape or something that they may be using in the network analysis topic to do double duty and look at your assembly graphs. There's also a couple of FASTA files that were output here. One is this one, before repeat resolution. So if you are interested in looking at the various stages of the assembly, you can look at it in this order. Before repeat resolution is kind of the earliest step that it outputs. The contigs.fasta is the second step that it outputs, and then scaffolds.fasta is the final assembly that includes all of the information. So we can take a look at that. It outputs the node number, the length of the node, and then the k-mer coverage of each one into your FASTA file. And that's what you'll use for your downstream analysis, probably, of functional annotation if you're going to input this into Proca or something for annotation. Then a lot of times you'll want to use those longer scaffolds, and probably also the ones that you'll want to submit to GenBank. Okay, so if you're doing this from home, you can finish running this loop and compare the different assemblies. I'm just going to run this real quick. If it works. Sorry, I had to go down one directory. So this is a program stats wrapper that's built into BB tools, and it's for looking at some statistics of your assemblies. And so we'll talk about this more in a later lesson. I just wanted to show what you can get out of these. So this is looking at each of those 3 different FASTA files, the before RR, contigs, and scaffolds. And you can do simple things like comparing the number of scaffolds in each one, the number of contigs, the N50s, the N90s, all of these metrics, which we will talk about at a later time, in order to compare the quality of the assemblies that you get. Like I said before, one of the techniques we often use is to just run a bunch of assembly pipelines with different parameters and then compare the outputs and pick the best one for going into our downstream analysis pipeline. And that's a very valid way to do this at the moment because there are no real gold standards for a lot of these things, especially in metagenomics. So there's still a lot of exploration to be done. One thing I would caution you, if you're a first-year master's or PhD student, please, please, please do not spend an entire year of your program optimizing to get the very best possible assembly that you can get, unless your question is how can we optimize to get the very best assembly? Because probably your question is a scientific question about what's going on in the environment. And in that case, you can probably just use what other people in your field or your environment are using and be pretty confident that you're going to get a good result. It's very easy to go down very long rabbit holes, very deep rabbit holes of optimization that's in the end turns out to be more or less unnecessary. So that's just a little bit of warning that I would give if you're tempted to dive into that rabbit hole. Okay, with that, I'm going to wrap it up for this time and then keep you informed about some upcoming lessons that will go into the visualization of that GFA file in a little bit more detail next time, and then look a little bit more at the statistical metrics that come out of the things like stats tool and Quast, which is another tool that we will use to look at the quality of our assemblies. And with that, I'll stop and ask if there's any more questions.